Hello, and welcome to Science for Sleep. I'm so glad you found your way here tonight. Maybe you're already tucked in, the day's weight lifting from your shoulders, the room dim and quiet around you. Maybe you're settling into that soft space between waking and dreaming, where thoughts can wander freely, untethered from the demands of tomorrow. Whatever brought you here, I've created this gentle pocket of the night just for you. A place where wonder and rest can exist together, where the biggest mysteries of the universe can be explored with the smallest, softest voice. Tonight, we're going to drift together into one of theoretical physics' most beautiful puzzles. Not with urgency, not with the need to solve or understand completely, but with the same gentle curiosity you might feel watching clouds form shapes against a darkening sky. We're going to explore white holes, the theoretical twins of black holes, the cosmic mirrors that might not exist at all but in their very possibility teach us something profound about the universe we inhabit. Now, I should tell you, I've done my best to make this journey as soothing and sleepy as possible, but theoretical physics, even whispered, even wrapped in metaphor, has a way of lighting up the mind. So if you find yourself more awake with wonder than drifting towards sleep, that's okay too. Your mind will eventually settle, like snow on a quiet evening, a little richer for having wondered. If you're already enjoying this quiet moment, I'd love it if you gave this video a gentle like, maybe even subscribe if you'd like more of these sleepy science stories, and if you're listening from somewhere special, a city apartment with rain on the windows, a cottage by the sea, or just your familiar bed that knows the shape of your dreams, let me know in the comments. I love picturing all the different places where people pause to wonder about the universe. This video, like all my others, is for relaxation and education only. It's not medical advice, not a replacement for professional help with sleep. It's just a peaceful place to let your mind float among the stars and theoretical possibilities. So now, let's begin. Take a slow breath. Let your body sink a little deeper into rest, and let's wonder together about something that might not exist at all, but in not existing, tells us everything about what does. Somewhere in the mathematics of the universe, in the quiet equations that describe how space bends and time flows, there lives a secret. Not a dark secret, but a bright one. So bright, in fact, that it might blind us to its possibility. It's the secret of symmetry, of mirrors, of things that come in pairs. You already know about black holes, those places where gravity wins so completely that nothing, not even light, can escape. Where space curves inward like a drain that never empties, where time slows and stops at a boundary we call the event horizon. Black holes are real. We've seen their shadows, felt their gravitational waves, watched stars dance around their invisible mass. But what if I told you that hidden in the very same equations that predict black holes, there's a prediction for something else? Something that is everything a black hole is not. A cosmic opposite. A mirror image written in mathematics. These theoretical objects are called white holes, and they are perhaps the strangest things physics has ever whispered about. Imagine standing before a mirror in the soft light of dawn. You raise your right hand, and your reflection raises its left. You step forward, it steps forward too, but into the opposite space, the reflected world behind the glass. This is how white holes exist in physics, as reflections of black holes, but reflections that follow their own strange rules. Where a black hole pulls everything in, a white hole would push everything out. Where a black hole has an event horizon that nothing can escape, a white hole would have an event horizon that nothing can enter. Where a black hole is the ultimate ending, a white hole would be the ultimate beginning. They are theoretical twins, born from the same mathematics but living completely opposite lives. This idea doesn't come from science fiction or wild imagination. It comes from the sober, careful mathematics of general relativity. When Carl Schwarzschild first solved Einstein's equations in 1916, creating the mathematical description of what we now call black holes, he found something unexpected. The equations had two solutions, not one. Like a quadratic equation that gives you both a positive and negative answer, the mathematics of curved space-time gave us both black holes and white holes. For black holes, we found evidence. We see them pulling apart stars, bending light, creating ripples in space-time when they merge. But for white holes, we look, and the universe seems silent about its bright secret. They remain purely theoretical, living only in the pristine world of mathematics, never stepping into the messy reality of space. Yet their theoretical existence teaches us something profound. The universe, at least in its mathematical bones, believes in balance. For every pull, there might be a push. For every ending, a beginning. For every shadow, perhaps somewhere, there could be a light. Think about this as you lie there in the darkness. Your room has its own symmetries. The wall to your left mirrors the wall to your right. The ceiling above reflects in a way the floor below. Even your breath has symmetry. In and out, rise and fall, a constant exchange between you and the air around you. The universe too might breathe in these symmetries, these mathematical pairs that help us understand not just what is, but what could be. White holes, if they exist, would be the universe exhaling, not breathing in like black holes do, gathering matter and light into themselves, but breathing out, pushing space and time and energy away from their hearts. They would be fountains in the fabric of space-time, springs that never run dry, sources that never empty. But how can something push everything away? How can there be a place in the universe that nothing can approach? To understand this, we need to dive deeper into what a white hole really means, into the strange physics of time running backward, into the mathematics that allows for such beautiful impossibilities. As you rest there, perhaps you can feel your own boundaries, where your body ends and the bed begins, where your thoughts fade into the quiet of the room. Black holes and white holes are about boundaries too, about the edges where the normal rules break down, where the universe shows us its limits and perhaps its infinite creativity. The mirror in the dark isn't just about reflection, it's about possibility. It's about the universe keeping its options open, writing into its very laws the chance for opposites, for balance, for things we haven't yet learned how to see. Let's float now into the heart of this mystery. What would a white hole be if it existed? Not in metaphor, not in poetry, but in the actual fabric of space and time. To understand this, we need to think about everything backward, to imagine a universe running in reverse, to picture the impossible with the same gentle attention we give to dreams. A white hole would be a region of space-time where nothing can enter. Think about that for a moment. We're used to barriers that keep things in, walls, containers, even black holes. But a barrier that keeps everything out, that's harder to picture. Yet that's exactly what a white hole would be. A cosmic force field, an ultimate repulsion, a place where space itself says no. Imagine you're trying to walk toward a white hole. As you get closer, something strange happens. No matter how hard you try to move forward, space itself pushes you back. Not violently, not with force you can feel, but inevitably. It would be like trying to walk up a hill that gets steeper with every step, until eventually the hill becomes a wall, then more than a wall, an impossibility. You could fire rockets, use all the energy in the universe, and still you could never cross that threshold. This boundary, like the event horizon of a black hole, would be invisible. There would be no wall to see, no barrier to touch. Just a region where the geometry of space-time itself forbids entry. But unlike a black hole's event horizon, which is a one-way door inward, a white hole's horizon would be a one-way door outward. Things can leave, but nothing can arrive. And here's where it gets even stranger. Inside a white hole, time would run backward. Not in the science fiction sense of people getting younger or broken glasses reforming, but in the deep mathematical sense that the arrow of causation points the opposite way. In our normal universe, causes come before effects. You drop a glass, then it breaks. You light a match, then it burns. But in a white hole, effects would come before causes. The mathematics insists on it. This backward flow of time is why white holes would push everything out. Just as things naturally fall into black holes because that's the forward direction of time near them, things would naturally fly out of white holes because that's their version of forward, which is our backward. It's as if the white hole exists in a bubble where the universe's movie is running in reverse, and anything inside that bubble must flow with that reversed current. What would emerge from a white hole? In theory, anything. Energy, matter, light, even information. It would be like a cosmic fountain that never needs refilling, a source that violates our everyday understanding of where things come from. The matter emerging wouldn't be created from nothing. It would have always been there, in the white hole's past, which is our future. Your mind might resist this idea, and it should. It goes against everything we experience. But mathematics doesn't care about our comfort. The light from a white hole would be extraordinary. While light falling into a black hole gets redshifted, stretched to longer wavelengths until it fades to invisibility. Light emerging from a white hole would be blue shifted. It would gain energy, climbing up the gravitational hill with ease, arriving at our telescopes brighter and more energetic than when it left. A white hole would glow, not from heat or fusion like a star, but from the simple fact of its existence, from its rejection of the outside universe. This glow wouldn't be steady like a star's. As matter and energy emerge from the white hole, they would create a kind of shock wave at the boundary. The emerging material would crash into any matter trying to fall in, creating a blazing shell around the white hole. This collision between the outward flow and the universe's attempt to flow inward would generate tremendous energy, making white holes, if they exist, potentially the brightest objects in the universe. But this brightness might also be their doom. The instability at the boundary where outflowing material meets the inward pressure of the universe could destroy a white hole almost as soon as it forms. Like a soap bubble that's too perfect to last, a white hole might collapse under the universe's insistence that things should be able to fall, not just rise. Yet in their brief theoretical existence, white holes show us something profound about the nature of reality. They remind us that the laws of physics, as we understand them, are surprisingly even-handed. They don't prefer black over white, in over out, future over past. The equations themselves are time-symmetric, allowing for both possibilities with equal mathematical grace. As you lie there, breathing slowly, you're experiencing your own arrow of time. Your thoughts flow from past to future. Your breath moves from in to out. Your day has flowed from morning to this quiet night. A white hole would experience none of this. Its existence would be a constant outpouring, a perpetual rejection of the future in favour of an eternal past. Perhaps that's why we've never seen one. Our universe seems to have chosen a direction, picked an arrow of time, decided that things fall apart rather than spontaneously assembling. But the mathematics keeps both options open, like a door that swings both ways, even if we've only ever seen it swing one direction. Every idea in physics has a birthday, a moment when mathematics reveals something unexpected, when equations whisper a secret that nobody was looking for. The idea of white holes was born in 1916, in the middle of a war, in the mind of a soldier who was also one of the brightest physicists of his time. Karl Schwarzschild was serving on the Russian front when he received Einstein's papers on general relativity. While others were focused on survival, Schwarzschild found solace in mathematics. In the trenches between the horrors of war, he solved Einstein's equations exactly, something Einstein himself hadn't managed to do. And in that solution, hiding like a pearl in an oyster, were both black holes and white holes. Schwarzschild wasn't looking for either. He was simply trying to describe the space-time around a massive object, how space curves, how time bends, how gravity emerges from geometry. But when he wrote down his solution, he found something strange. The mathematics had two parts, mirror images of each other. One part described what we now call a black hole. The other part, when physicists finally understood it decades later, described a white hole. It's beautiful, really, how discovery works. Schwarzschild died just months after his discovery, never knowing that he had found the mathematical foundation for the most extreme objects in the universe. Einstein himself was skeptical. He thought the strange behaviour at what we now call the event horizon was a mathematical artifact, not a physical reality. It would take decades before physicists realised these solutions might describe real objects in space. The white hole part of Schwarzschild's solution was even more puzzling. While the black hole solution described the future, what happens to matter that collapses, the white hole solution described the past, a kind of cosmic explosion that has always been exploding, a source that has always been sourcing. Physicists filed it away as a mathematical curiosity, a quirk of the equations with no physical meaning. But mathematics has a way of being patient. It waits for us to catch up, to develop the tools and concepts needed to understand what it's been telling us all along. In the 1960s, as physicists developed better ways to understand space-time, they returned to Schwarzschild's solution with fresh eyes. They found that if you follow the mathematics carefully, if you trace the path through curved space-time, you inevitably arrive at white holes. The key insight came from thinking about space-time as a whole, not just space evolving in time. When you draw a diagram of space-time around a black hole, with space on the horizontal axis and time on the vertical, you see the characteristic funnel shape that traps light and matter. But the mathematics insists this funnel has two parts. The part we see, where things fall in, and another part hidden in the past where things must flow out. This wasn't wishful thinking or theoretical playfulness. It was what the equations demanded. Just as the square root of 4 gives you both plumb 2 and 2, the equations of general relativity give you both black holes and white holes. You can't have one without the other, at least not in the pure mathematics. Roger Penrose, one of the pioneers in understanding these solutions, showed that white holes were the time reverse of black holes. If you could film a black hole and play the movie backward, you'd see a white hole. Matter falling in becomes matter flying out. Light trapped becomes light released. The point of no return becomes the point of no approach. But here's where the story takes a turn. While black holes can form naturally, we understand how a massive star collapses, how gravity overwhelms all other forces, how an event horizon forms and grows. Nobody could figure out how a white hole could form naturally. They seemed to require initial conditions that made no sense, like asking for an egg to unbreak itself or smoke to flow back into a chimney. This is the eternal tension in theoretical physics. The mathematics gives us possibilities, but nature chooses which possibilities to realize. The equations are democratic, but the universe seems to have preferences, and one of those preferences appears to be for black holes over white holes, for endings over beginnings, for gravity that gathers rather than repels. Yet physicists couldn't quite let go of white holes. They were too beautiful, too perfect a solution to abandon entirely. If the universe allows black holes, and if the mathematics insists on symmetry, then somewhere, somehow, shouldn't white holes exist too? This question led to some of the most creative thinking in physics, to new ways of understanding time, causality, and the nature of existence itself. As you rest there in the quiet night, you're surrounded by asymmetries. Your heart beats, but doesn't unbeat. Your thoughts flow forward, but don't flow backward. The very fact that you can remember the past but not the future is a kind of cosmic choice, a breaking of the symmetry that mathematics allows. White holes live in the symmetric world of equations, while we live in the asymmetric world of experience. But perhaps that's what makes them so fascinating. They show us a universe that could have been, a road not taken, a possibility that remains forever potential. In their non-existence, they teach us why things are the way they are. In their theoretical beauty, they show us the difference between what mathematics allows and what nature chooses. The birth of the white hole idea was really the birth of a question. Why does the universe prefer one solution over another? Why black but not white? Why in but not out? Why future but not past? These questions, born in the trenches of World War I, still echo in physics departments today, still inspire wonder in those who dare to ask what else might be possible. Now let's drift deeper into the mirror world, into the strange symmetries that connect black holes and white holes. Imagine holding a perfect mirror up to space itself, reflecting not just light, but the very fabric of reality. What you'd see in that cosmic mirror is the domain of white holes, a place where every rule is reversed, every flow inverted, every impossibility made manifest. In a black hole, space flows inward like a river approaching a waterfall. The closer you get to the event horizon, the faster space itself moves toward the center. Once you cross that horizon, the flow becomes irresistible. Space carries you to the singularity like a current too strong to swim against. This isn't a force in the traditional sense. It's the shape of space itself, curved so severely that all paths lead inward. Now flip that image. In a white hole, space flows outward. The event horizon isn't a point of no return, but a point of no approach. Space itself pushes away from the center, carrying everything with it like a spring that never stops bubbling up. The closer you try to get, the stronger the outward flow becomes, until at the horizon itself, space is moving outward at the speed of light. Nothing, not even light, can swim upstream against that flow. This is hard to picture because we never see anything like it in daily life. We're used to things that pull, gravity, magnets, the drain in your bathtub, but something that pushes eternally, that creates an impenetrable barrier not through solidity but through the pure geometry of space. That's the looking glass world of white holes. The symmetry goes deeper than just the direction of flow. In a black hole, time itself points inward. Once you cross the event horizon, moving toward the singularity isn't just inevitable, it's your future. The singularity isn't a place you're moving toward in space, it's a moment you're moving toward in time. That's why escape is impossible. You can no more avoid the singularity than you can avoid tomorrow. In a white hole, this too is reversed. The singularity exists in the past, not the future. It's not where you're going, but where everything came from. The outward flow isn't just a movement in space, but a movement in time, away from that initial moment, that eternal yesterday that defines the white hole's existence. Everything inside a white hole is fleeing from its own past, riding the current of time that, in this reversed region, points outward instead of inward. This temporal reversal is perhaps the hardest thing to grasp about white holes. We're so used to cause preceding effect, to the past determining the future, that a region where this is backward seems like pure fantasy. But the mathematics doesn't distinguish. In the equations of general relativity, time is just another coordinate like north or east. And just as you can travel north or south, the equations allow for regions where time's arrow points in unusual directions. There's a beautiful diagram physicists use to understand this called a Penrose diagram. It's like a map of space-time, compressed and distorted so you can see the whole eternal structure at once. On this map, a black hole looks like a triangle pointing to the future. Everything that enters must reach the singularity at the triangle's apex. A white hole is the same triangle pointing to the past. Everything inside must leave, flowing away from the singularity at its base. But here's where the symmetry becomes even more intriguing. In the full mathematical solution, black holes and white holes aren't separate objects. They're connected, two parts of the same eternal structure. The complete Schwarzschild solution includes both, linked by what physicists call an Einstein-Rosen bridge, a wormhole connecting the black hole region to the white hole region. In this complete picture, matter falls into the black hole, travels through the wormhole and emerges from the white hole. It's like a cosmic recycling system, a universe that takes in through one door and releases through another. The symmetry is perfect, the mathematics elegant, the concept breathtaking. But, and there's always a but in physics, this connection exists only in the idealized mathematical solution. In reality, any wormhole between a black hole and white hole would be unstable, collapsing faster than light could traverse it. The symmetry that exists in the timeless world of mathematics breaks in the time-bound world of reality. Still, the looking glass teaches us something profound. It shows us that the universe's laws are more flexible than our experience suggests. Direction is not absolute. Time's arrow is not carved in stone. The universe allows for regions that violate our common sense, even if it rarely or never creates them. As you lie there, you exist firmly on one side of the looking glass. Time flows forward for you. Gravity pulls rather than pushes. Causes precede effects. You can remember yesterday but not tomorrow. But in the mathematics that describes your universe, there's always that other solution, that mirror world where everything runs backward, where the impossible becomes inevitable. Perhaps white holes are the universe's way of reminding us that our perspective is limited. We see time flow one way because we're embedded in that flow. We experience gravity as attractive because we live in regions where it is. But the universe itself knows both directions, both possibilities. It writes them into its most fundamental laws, even if it chooses to manifest only one. The looking glass isn't just a curiosity. It's a window into the democratic nature of physical law, the even-handedness of mathematics, the way the universe keeps all options open even when it seems to choose just one. In every black hole, the ghost of a white hole lingers. In every inward flow, the possibility of an outward one exists. The mirror is always there, even when we can't see our reflection. Here we arrive at the heart of the matter, the question that keeps theoretical physicists awake at night. Not with worry, but with wonder. Can white holes actually exist? Not in the pristine world of mathematics, where they certainly do, but in the messy, chaotic, beautiful universe we inhabit. It's one thing for an equation to allow something. It's quite another for nature to build it. The challenge begins with birth. We understand how black holes are born. A massive star runs out of fuel, its core collapses, gravity wins over every other force, and an event horizon forms. It's violent but natural, like a thunderstorm or an avalanche. Extreme but following the universe's rules. We've watched it happen, seen the supernova, detected the gravitational waves. Black holes earn their existence through cosmic catastrophe. But how would a white hole be born? This is where the theory meets its first great obstacle. A white hole seems to require initial conditions that make no physical sense. It would need to already exist at the beginning of time, fully formed, ready to expel matter and energy for eternity. There's no collapse that creates a white hole, no process that forms one. They would have to be written into the universe's initial conditions, like finding a fully formed watch in the primordial soup. Even if a white hole somehow existed, it would face an immediate crisis. Remember, nothing can enter a white hole. Space itself pushes everything away. But the universe is full of stuff. Particles, radiation, cosmic dust, the gentle rain of matter that falls everywhere. All of this would pile up at the white hole's horizon, unable to enter but unable to escape the gravitational pull entirely. This creates what physicists call an instability. The matter would build up, layer upon layer, creating a shell of incredible density around the white hole. This shell would grow denser and hotter, radiation pressure building, until eventually, and this is the crucial part, the shell itself would collapse into a black hole. The white hole would be surrounded, smothered, transformed into its opposite. It's as if the universe has an immune system that rejects white holes, converting them into black holes as quickly as possible. The timescale for this transformation would be incredibly short. Some calculations suggest that even in the emptiest regions of space, a white hole would accumulate enough matter to trigger collapse in microseconds. Others are more generous, giving white holes perhaps a few minutes or hours before they are overwhelmed. But compared to the billions of years that black holes can survive, white holes would be mayflies, born only to die. There's another problem, perhaps even more fundamental. White holes violate our understanding of thermodynamics, specifically the second law, the one that says entropy always increases. Black holes have entropy. They're the ultimate in disorder, places where information is scrambled beyond recognition. But white holes would have negative entropy. They would spontaneously create order, spewing out organized matter and energy from nothing. It would be like watching a broken egg reassemble itself, smoke flow back into a chimney, or time itself running backward. The universe seems to have a deep preference for increasing entropy, for disorder over order, for futures that are more chaotic than their pasts. This isn't just a tendency, it appears to be a fundamental law, and white holes would violate this law with every particle they emit, every photon they release. They would be islands of decreasing entropy in a sea of increasing disorder. Yet, and here's where it gets interesting, some physicists haven't given up. They've proposed scenarios where white holes might briefly exist, perhaps in the extreme conditions of the early universe, when the normal rules were still settling into place, perhaps as quantum fluctuations, appearing and disappearing faster than we could ever detect, perhaps as the final stage of black hole evaporation, when quantum effects might convert a dying black hole into a short-lived white hole. These ideas remain highly speculative, more mathematical poetry than established physics. But they show how hard it is to completely rule out something that the equations allow. Nature might be more creative than we imagine, might find loopholes we haven't thought of, might occasionally permit the impossible. As you rest there, breathing steadily, you're surrounded by processes that only go one way. Your breath warms the air, but the air doesn't spontaneously cool to warm your lungs. Your thoughts flow from past to future, but never the reverse. The candle burns down, but never burns up. This one-way nature of reality is what makes white holes so alien, so unlikely, so fascinating. Perhaps white holes can't exist precisely because they're too perfect. They represent a kind of purity, pure outflow, pure reversal, pure violation of the universe's preferred direction. The universe we inhabit is messy, probabilistic, always increasing in entropy. White holes would be pristine fountains of order in a cosmos that prefers disorder. But the search continues. Every strange astronomical observation, every unexplained burst of energy, every anomaly in the cosmic data gets examined with the question, could this be a white hole? So far, the answer has always been no. Every candidate has turned out to be something else. A supernova, a gamma-ray burst, an active galactic nucleus. The universe offers us many wonders, but white holes, it seems, are not among them. Still, their theoretical existence serves a purpose. They mark the boundary between what mathematics allows and what nature permits. They show us that not every solution to an equation represents a possible reality. They teach us that the universe makes choices, has preferences, follows arrows that the equations themselves don't demand. In their probable non-existence, white holes tell us something profound about existence itself. They whisper that reality is more constrained than mathematics, that the universe has rules beyond the equations, that there are principles, like the forward flow of time and the increase of entropy, that shape what can be, not just what might be. Time. We swim in it, drift through it, are carried by it always forward, never back. It's the most familiar thing in the universe, and perhaps the most mysterious. And when we talk about white holes, we're really talking about time, about its direction, its flow, its stubborn insistence on moving from past to future. Tonight, let's float gently into this mystery, into why time has an arrow, and why that arrow seems to forbid white holes from existing. Close your eyes for a moment, and feel time passing. Your heartbeat marks it, your breath measures it, your thoughts flow through it. But what gives time its direction? Why does it move forward? Why can we remember yesterday but not tomorrow? These questions might seem philosophical, but they're at the heart of physics, at the core of why white holes remain theoretical while black holes fill the universe. The answer, surprisingly, isn't in the fundamental laws of physics. If you film a planet orbiting the Sun and play it backward, it still looks like a valid orbit. If you reverse the collision of two particles, the reverse collision obeys the same laws. At the deepest level, the equations of physics don't care about time's direction. They work equally well forward or backward. This is the time symmetry we've been dancing around, the mathematical democracy that allows both black holes and white holes. But something breaks this symmetry. Something chooses forward over backward, future over past. That something is entropy, the measure of disorder, of randomness, of the many ways things can be arranged. And entropy, unlike the fundamental laws, does have a preferred direction. It increases, always, without exception. Think of a sand castle on a beach. There's only one way for the grains to be arranged into a castle, but trillions of ways for them to be scattered. Leave the castle alone, and wind and waves will inevitably scatter the sand. You'll never see scattered sand spontaneously form into a castle. Not because it's impossible according to the laws of physics. Every grain could, in principle, move just right to build a castle. But because it's so incredibly unlikely that it might as well be impossible. This is entropy's arrow probability's preference. There are always more ways to be disordered than ordered, more ways to be mixed than separated, more ways to be random than structured. And so the universe, following the paths of probability, flows from order to disorder, from low entropy to high, from past to future. Black holes fit perfectly into this story. They're entropy machines, the ultimate in disorder. When matter falls into a black hole, its information is scrambled beyond recognition. All the details, what kind of matter it was, how it was arranged, its history and structure, are lost, replaced by the simple properties of mass, charge, and spin. Black holes have the highest entropy of any object in the universe. They represent the final victory of disorder. But white holes? They would run this process backward. They would take scrambled information and unscramble it, take disorder and create order, take high entropy and produce low entropy. Every particle emerging from a white hole would represent a decrease in entropy, a step backward in time's preferred direction. It would be like watching smoke flow back into a cigarette, like seeing shattered glass reform into a window. This is why the universe seems to reject white holes. They're not just rare or unlikely, they're swimming against the current of time itself. The same statistical laws that make your coffee cool down, that make perfume diffuse through a room, that make stars burn out and galaxies fade, also make white holes effectively impossible. But here's where it gets beautifully strange. The early universe had very low entropy. The Big Bang started with everything in a highly ordered state, hot, dense, but uniform. Since then, entropy has been increasing, creating the arrow of time we experience. But this raises a profound question. If the universe started in a low entropy state, isn't that itself like a white hole? A source of order in a cosmos that prefers disorder? Some physicists have proposed exactly this, that the Big Bang itself might be thought of as the ultimate white hole. Not a white hole in space, but in time. A cosmic boundary from which everything emerges, which nothing can precede, which spews forth matter and energy and space itself. The beginning of time might be the one white hole nature allowed, the single exception to its own rules. As you lie there in the gathering quiet of night, you're experiencing entropy's increase in countless small ways. The warmth of your body spreading into the cooler air, the orderly thoughts of the day dissolving into the randomness of dreams, the battery in your phone slowly draining, the candle burning down, the stars above converting hydrogen to helium and light. Everything flows in one direction, from available energy to unavailable, from order to disorder, from past to future. This flow is what makes memory possible. We remember the past because it had lower entropy. fewer possible arrangements. We can't remember the future because it has higher entropy, more possible arrangements. The arrow of time isn't just a physical law, it's the foundation of consciousness, of causality, of the very notion of before and after. White holes would exist outside this arrow, or rather, they would point their own arrow backward. Inside a white hole, entropy would decrease, time would run reversed, effects would precede causes. It would be a bubble of backward time in a forward-flowing universe, and like all bubbles, it would be fragile, temporary, doomed to pop. Yet the fascination remains. In their impossibility, white holes illuminate possibility. They show us that time's arrow, so fundamental to our experience, is not written into the deepest laws. It emerges from statistics, from probability, from the simple fact that there are more ways to be random than organized. The universe chose its direction not through divine decree but through the democracy of disorder. Perhaps somewhere in the vast cosmos, in regions we haven't yet observed, in conditions we haven't yet imagined, entropy might occasionally flow backward. Perhaps white holes exist for nanoseconds in quantum fluctuations, or in the hearts of the strangest stars, or in the moments just after black holes die. These would be miracles of physics, not supernatural, but supremely natural, representing possibilities so rare they border on the impossible. Time's arrow flies straight and true through the universe, carrying us all from birth to death, from order to disorder, from Big Bang to heat death. But in the mathematics that describes this flight, there's always that other solution, that reverse trajectory, that white hole waiting in the equations like a road not taken. And in that waiting, in that theoretical existence, we find a deeper appreciation for why time flows as it does, why the universe unfolds rather than folds, why we are creatures of memory rather than prophecy. Let's drift now to the edge of everything, to the moment when time itself began, to the greatest mystery in all of cosmology. Because if we're searching for a white hole, a place where matter and energy emerge, where nothing can return, where the arrow of time points outward, we might not need to look any further than our own beginning. The Big Bang itself might be the ultimate white hole, the one exception to nature's rules, the cosmic fountain from which everything flows. Think about what we know of the Big Bang. It wasn't an explosion in space. It was an explosion of space. Every point in the universe was once compressed into a singularity, a moment of infinite density and temperature. And from that moment everything emerged. Space itself expanded, time began its forward flow, matter and energy rushed outward in all directions. Nothing can go back to before the Big Bang, just as nothing can enter a white hole. The parallels are striking. A white hole has a past singularity from which everything emerges. The Big Bang is a past singularity from which everything emerged. A white hole spews matter and energy outward. The Big Bang spewed matter and energy outward. A white hole represents a boundary in time that cannot be crossed. The Big Bang represents the ultimate boundary in time. There is no before to return to. Some cosmologists have taken this idea seriously. They've proposed that our universe might literally be the inside of a white hole. Not a white hole sitting somewhere in space, but a white hole in a higher dimensional reality. Just as matter falling into a black hole in our universe might emerge from a white hole in another, perhaps our entire cosmos is matter, emerging from a white hole in some parent universe. This isn't just poetic speculation. The mathematics of general relativity allows for such solutions. You can write down equations where a collapsing star in one universe creates a black hole, and that black hole's interior becomes a new expanding universe. A Big Bang, a white hole birth of space and time. Each black hole might birth a baby universe. Each universe might contain black holes that birth more universes, an endless genealogy of cosmic creation. But there's a crucial difference between the Big Bang and a typical white hole. A white hole in space would be unstable, quickly accumulating matter at its horizon, until it collapsed into a black hole. The Big Bang, being a white hole in time rather than space, doesn't face this problem. There's no external universe trying to fall into it. There's no accumulation of matter at its boundary. It can expand forever, stable and eternal, the one white hole that nature permits because it is nature. As you rest there in the darkness, you're inside this cosmic white hole. Every atom in your body emerged from that initial singularity. The space you occupy expanded from that first moment. The time flowing through your thoughts began its flow then. You don't just live in a universe that had a Big Bang. You live in the Big Bang, still expanding, still evolving, still flowing outward from that initial moment. This perspective changes everything. Instead of white holes being impossible objects that violate the laws of thermodynamics, the entire universe becomes a white hole that defines those laws. The arrow of time doesn't forbid white holes. It's created by the ultimate white hole. Entropy increases not despite our white hole universe, but because of it, as the cosmos expands and cools and disorders itself in the outward flow from the bang. Think about the cosmic microwave background, that faint glow of radiation left over from the early universe. It's the light from when the cosmos was young and hot, stretched by billions of years of expansion. In white hole terms, it's the glow of matter and energy emerging from the cosmic white hole, the afterglow of creation itself. We don't just theorize about white hole radiation, we bathe in it every moment of every day. The expansion of the universe takes on new meaning in this view. Galaxies aren't just moving apart because of some initial push. They're moving apart because space itself is emerging, flowing outward from the Big Bang white hole. Dark energy, that mysterious force accelerating the expansion, might be the white hole's persistent push, the cosmic pressure that keeps everything flowing outward. Even black holes fit into this picture beautifully. In a universe that is itself a white hole, black holes become not opposites but complements. They're regions where the outward flow reverses, where space falls inward, where the cosmic white hole develops tiny wounds that heal themselves by swallowing matter. The universe breathes out everywhere except at black holes, where it breathes in. This cosmic white hole view also addresses one of the deepest puzzles in cosmology. Why did the universe begin in such a low entropy state? If the universe is a white hole, it must begin with low entropy. That's what white holes do. They're sources of order in a cosmos that tends toward disorder. The Big Bang's low entropy isn't a mystery to be solved, but a necessary feature of its white hole nature. Of course, this remains speculation, beautiful and mathematically consistent but unproven. We can't observe the universe from outside to see if it's truly a white hole. We can't probe before the Big Bang to understand what, if anything, created our cosmic fountain. But the possibility itself is illuminating. It suggests that white holes aren't forbidden by nature. We might be living inside one. As you drift towards sleep, consider this. Every breath you take expands the universe a little bit more. Every moment that passes carries you further from the cosmic singularity. You're not just in the universe, you're part of its expansion, part of its emergence, part of the greatest white hole of all. The cosmos doesn't just contain you, it emerges with you, a 14 billion year fountain of space and time and possibility that shows no sign of running dry. Perhaps we've been searching for white holes in the wrong places. Instead of looking for them in distant galaxies or theoretical equations, we should recognize that we're inside one. The Big Bang isn't just similar to a white hole, it might be the only white hole nature needs, the single source from which all sources flow, the one reversal of time's arrow that makes all other arrows possible. Now we venture into even stranger territory, into the theoretical passages that might connect black holes to white holes, into the shortcuts through space-time that have captured imaginations for decades. These are wormholes, not holes made by worms, but tunnels through the fabric of space itself, cosmic bridges that could, in principle, connect any 2 points in the universe. and at the heart of wormhole physics lies the intimate relationship between black holes and white holes. The idea emerged in 1935 when Einstein and his colleague Nathan Rosen were studying the mathematics of black holes, though they weren't called that yet. They discovered something remarkable. The complete solution to their equations didn't just describe a black hole, it described a bridge, a tunnel through space-time connecting two separate regions. On one end was a black hole, on the other end was a white hole. The Einstein-Rosen bridge was born. Picture space-time as a folded sheet of paper. Normally, to travel from one side to the other, you'd have to traverse the entire surface, but if you could punch a hole through the fold, you'd have a shortcut. That's what a wormhole represents. Not just a hole, but a tunnel, a passageway that connects distant regions through a higher dimension. And according to Einstein and Rosen's mathematics, every black hole might be one mouth of such a tunnel. In this picture, matter falling into a black hole doesn't simply disappear into a singularity. Instead, it travels through the wormhole and emerges from a white hole somewhere else. The black hole is the entrance, the white hole is the exit, and the wormhole is the cosmic subway connecting them. It's an elegant solution that avoids the messiness of singularities, those points where physics breaks down. Instead of matter being crushed to infinite density, it simply passes through. But, and you knew there would be a but, these wormholes have a fatal flaw. They're unstable, catastrophically unstable. The mathematics shows that any Einstein-Rosen bridge would collapse faster than light could traverse it. The tunnel would pinch off, the connection would sever, and anything trying to pass through would be crushed in the collapse. The bridge exists in the mathematics, but it's a bridge that falls before anyone can cross it. Think of it like a soap bubble. The mathematics allows for a perfect spherical bubble, and indeed bubbles can form, but they're fragile, temporary, doomed to pop. Einstein-Rosen bridges are similar, mathematically perfect but physically ephemeral. They represent a possibility that nature seems to forbid in practice. This instability is directly related to the nature of white holes. Remember, white holes push everything away, while black holes pull everything in. At the junction of a wormhole, these opposing tendencies meet. The result is a kind of cosmic tug-of-war that the structure can't survive. The inward pull of the black hole and the outward push of the white hole tear the bridge apart from within. As you lie there in the quiet darkness, you might wonder, could anything stabilize a wormhole? Could nature find a way to prop open these cosmic shortcuts? Theoretical physicists have explored this question for decades, and they've found some intriguing possibilities. The key is something called exotic matter. Matter with negative energy density. Matter that pushes rather than pulls. Matter that we've never observed but that physics doesn't explicitly forbid. With enough exotic matter, you could, in principle, hold a wormhole open. The negative energy would counteract the tendency to collapse, creating a stable tunnel through space-time. But this isn't ordinary matter. It would have to violate energy conditions that normal matter always obeys. It would be like anti-gravity, pushing outward where gravity pulls inward. Some physicists have proposed that quantum effects might provide this exotic matter. In the quantum world, energy can fluctuate, becoming negative for brief moments in tiny regions. Perhaps these quantum fluctuations could stabilize microscopic wormholes, creating a foam of tiny tunnels at the smallest scales of space-time. But scaling this up to a traversable wormhole, one that a person or even a particle could pass through, seems to require more exotic matter than the universe contains. There's another profound issue with wormholes connecting black holes to white holes: causality. If you could travel through such a wormhole, you wouldn't just be taking a shortcut through space, you'd be travelling through time. The white hole end exists in the past of the black hole end. Traversing the wormhole would be like travelling backward in time, potentially creating paradoxes that physics abhors. Imagine dropping a ball into a black hole, having it emerge from a white hole in the past, and then preventing yourself from dropping it in the first place. This kind of causal loop, where effects precede their causes, seems to be something the universe strictly forbids. It's another way that nature says no to traversable wormholes, another lock on a door that mathematics left open. Yet the dream persists. In science fiction, and in the hearts of theoretical physicists, wormholes represent the ultimate possibility: instant travel across the cosmos, shortcuts through the vastness of space, connections between otherwise isolated regions of the universe. And while the wormholes connecting black holes to white holes seem impossible, other types of wormholes might be more forgiving. Wormholes connecting two regions of normal space without the complication of white holes might be easier to stabilize, though still far beyond our current capabilities. The search for wormholes continues in subtle ways. Some physicists look for their signatures in astronomical observations, peculiar gravitational lensing effects, unusual patterns in the cosmic microwave background, or strange behaviors of light from distant sources. So far, space seems smooth, without the shortcuts that wormholes would provide, but absence of evidence, as they say, isn't evidence of absence. What wormholes teach us, whether they exist or not, is that space is more flexible than our daily experience suggests. It can bend, fold, and potentially connect in ways that defy intuition. The fact that Einstein's equations allow for such structures, even if nature doesn't build them, expands our conception of what space-time really is. It's not just a stage on which events occur, it's a dynamic geometric entity capable of forming structures we can barely imagine. As you rest there, perhaps you can imagine space folding gently around you, not dramatically enough to form a wormhole, but enough to remind you that the geometry of the universe is subtle and deep. Every mass curves space a little, every movement sends out ripples, every moment is connected to every other through the flexible fabric of space-time. Wormholes might be impossible, but the space that would contain them is real, and it's stranger than we often appreciate. Let us drift now into one of the deepest mysteries in physics, a puzzle that connects black holes, white holes, and the very nature of reality itself. It's called the information paradox, and it might hold the key to understanding whether white holes could ever exist, even for the briefest moment. This paradox touches on questions so fundamental that they challenge our understanding of what it means for something to exist, to disappear, or to transform. Information, in physics, isn't about words or data in the conventional sense. It's about the complete description of a physical system, the position and velocity of every particle, the quantum state of every field, all the details that make something what it is. One of the bedrock principles of quantum mechanics is that information is conserved. It can be scrambled, encrypted, transformed beyond recognition, but it can never be truly destroyed. Black holes seem to violate this principle. When matter falls into a black hole, all its information appears to vanish. The black hole only remembers three things about what it swallowed: mass, electric charge, and angular momentum. Everything else, whether it was a star or a pile of encyclopedia, whether it was hot or cold, whether it was made of matter or antimatter, all these details seem to disappear forever behind the event horizon. This is troubling enough, but Stephen Hawking made it worse. In 1974, he discovered that black holes aren't perfectly black. They emit radiation, now called Hawking radiation, a slow quantum leak of particles from just outside the event horizon. This radiation appears to be completely random, containing no information about what fell into the black hole, and eventually, after eons, the black hole evaporates completely through this radiation, seemingly taking all the trapped information with it into oblivion. This is the information paradox. Quantum mechanics says information can't be destroyed, but black holes seem to destroy it. It's not just a technical problem, it strikes at the heart of physical law. If information can be destroyed, then quantum mechanics is wrong. If it can't be destroyed, then our understanding of black holes is incomplete. Something has to give. Enter white holes. Some physicists have proposed a radical solution to the information paradox. What if black holes don't destroy information because they eventually become white holes? In this scenario, a black hole swallows matter and information for billions of years, then through some quantum process we don't yet understand, transforms into a white hole that releases everything back out. This wouldn't be a simple reversal. The information would be scrambled beyond recognition, encrypted in the quantum radiation, spread across space and time in ways that make it practically impossible to decode. But it would be there, preserved, conserved, satisfying the laws of quantum mechanics while respecting what we know about black holes. The transformation would happen at the end of the black hole's life, when Hawking radiation has reduced it to the smallest possible size. At this point, quantum effects dominate over classical gravity. The smooth space-time of general relativity gives way to the fuzzy, probabilistic world of quantum mechanics. And in this quantum regime, perhaps the impossible becomes possible, a black hole bouncing into a white hole like a ball hitting the ground and reversing direction. This idea comes from a theory called loop quantum gravity, one of the attempts to unify quantum mechanics with general relativity. In this theory, space itself is quantized, made of tiny, discrete loops rather than smooth continuum. When a black hole shrinks to the size of these loops, the theory suggests it might undergo a quantum bounce, reversing from inward collapse to outward expansion, from black hole to white hole. The white hole phase would be brief, perhaps lasting only microseconds before the outpouring of matter and energy disperses into space. But in those microseconds, all the information that fell into the black hole over its lifetime would be returned to the universe. Not in any useful form. It would be like trying to reconstruct a burned book from its smoke and ashes, but returned nonetheless, preserving the sacred principle of information conservation. As you rest there in the gathering quiet, you're surrounded by information. Every atom in your body, every photon of light, every whisper of air carries information about its history, its interactions, its quantum state. This information might be scrambled, encrypted by countless interactions, but it's there. The universe remembers everything, even if that memory is hidden in the dance of particles and waves. The connection between white holes and information runs deeper still. If white holes are regions where time runs backward, then they're also regions where information flows backward. In our normal, forward time universe, information spreads out, becomes more scrambled, more encrypted. In a white hole, information would concentrate, becoming more ordered, more pristine. It would be like watching smoke gather into a cigarette, like seeing ripples on a pond converge to recreate the dropped stone. This backward flow of information is another reason why white holes seem impossible in our universe. They would represent not just a reversal of time, but a reversal of information's natural tendency to spread and scramble. They would be islands of decreasing entropy in an ocean of increasing disorder, cosmic computers running in reverse, uncomputing the history of everything that enters them. Yet the information paradox demands some kind of resolution. If not white holes, then what? Some physicists propose that information is encoded on the black hole's horizon, smeared across the boundary in a cosmic hologram. Others suggest that black holes connect to other universes, shunting information elsewhere rather than destroying it. Still others question whether information conservation is truly fundamental, whether the universe might occasionally allow for genuine loss. The debate continues, with each proposed solution revealing new mysteries. But the possibility of black holes becoming white holes remains tantalizing. It would be poetic, the universe's ultimate recycling program, where nothing is lost, only transformed. Black holes would become not graves but chrysalises, holding information in cosmic cocoons until they're ready to release it as white holes. Perhaps every black hole death is also a white hole birth, too brief for us to observe, too scrambled for us to decode, but real nonetheless. Perhaps the universe is full of these quantum flashes, these momentary fountains where information returns from the edge of oblivion. We haven't seen them because we haven't known where or how to look, or because they last for such brief moments that they escape our notice. The information paradox teaches us humility. Despite our equations and observations, despite our theories and instruments, we still don't fully understand what happens to information in the universe's most extreme environments. White holes, whether they exist or not, represent one possible answer. A way for the universe to balance its books, to ensure that every bit of information is accounted for, even if it takes a journey through the impossible to return home. We drift now into the smaller scales of reality, where space itself becomes grainy, and time loses its smooth flow. Here, in the quantum realm, the impossible might find a way to exist. Because at the tiniest distances, shorter than atoms, smaller than particles, more minute than anything we can directly observe, the universe plays by different rules, and in those different rules, white holes might find their chance to shine, if only for the briefest moment. Loop quantum gravity, one of our best attempts to describe space at its most fundamental level, suggests that space-time isn't smooth like we imagine. Instead, it's woven from tiny loops, discrete threads of space and time that can't be subdivided further. It's like discovering that a seemingly smooth fabric is actually made of individual fibers, or that a continuous movie is really a series of still frames. At the smallest scale, reality is pixelated. In this pixelated space-time, something remarkable might happen to black holes. As they evaporate through Hawking radiation, they shrink smaller and smaller. Eventually, they reach the scale of the quantum loops themselves. And here, the theory suggests, they can shrink no further. The collapse that created the black hole reaches its absolute limit. The inward fall stops not because something blocks it, but because there's no more inward to fall into. What happens next is beautiful and strange. Like a ball compressed to its limit and then released, the black hole bounces. The collapse reverses into expansion. The inward flow becomes outward. The black hole transforms into a white hole. All the matter that fell in over millions or billions of years comes rushing out, compressed into a quantum explosion lasting microseconds. It's cosmic rebirth at the smallest possible scale. This isn't just wild speculation. The mathematics of loop quantum gravity predicts this bounce, demands it even. The equations that describe the quantum loops of space simply don't allow for infinite compression. When the density reaches about 10 to the 96 times the density of water, a number so large it defies comprehension, the collapse must stop and reverse. The universe has a basement, and when you hit it, you bounce. But here's where quantum mechanics adds its own twist. The bounce wouldn't be simple or predictable. Quantum uncertainty would scramble everything, adding a fundamental randomness to what emerges. The white hole wouldn't just spit out what the black hole swallowed. It would release a quantum remix, information preserved but encrypted beyond recognition, matter transformed by its journey through the quantum underworld. The timescale is crucial. While a black hole might live for billions of years, its white hole phase would last perhaps 10 to 40 seconds, a duration so short that light itself barely has time to move. In that impossibly brief moment, all the mass of the black hole would emerge, creating a flash of energy that might be visible across the universe. Some physicists have suggested that mysterious gamma-ray bursts, brief, intense flashes of radiation we observe from distant galaxies, might be these quantum white holes announcing their brief existence. As you breathe quietly in the darkness, quantum processes are happening all around you and within you. Particles pop into existence and annihilate. Uncertainty principles blur the edges of reality. The quantum world is one of possibilities and probabilities, where the impossible happens regularly as long as it happens briefly enough. White holes might be another example of this quantum permission for the forbidden, allowed to exist as long as they don't overstay their welcome. This quantum perspective also changes how we think about the relationship between black holes and white holes. They're not separate objects, but different phases of the same object. A star collapses into a black hole, the black hole evaporates and bounces into a white hole, the white hole explodes and disperses. It's a complete life cycle, from concentration to dispersion, from order to disorder, from past to future, all mediated by the quantum nature of space itself. The uncertainty principle plays a crucial role here. In quantum mechanics, you can't know both the position and momentum of a particle perfectly. Similarly, at the quantum scale, you can't perfectly define both space and time. This fundamental fuzziness might be what allows the black-to-white transformation. In that quantum fog, the universe momentarily forgets which direction time should flow, allowing for the reversal that creates a white hole. There's something deeply satisfying about this picture. It suggests that nothing in the universe is truly permanent, not even black holes. Everything transforms, everything changes, everything eventually returns its borrowed matter and energy to the cosmic commons. Black holes aren't graves but temporary vaults, holding matter until quantum mechanics picks the lock and releases it as white holes. But detecting these quantum white holes would be extraordinarily difficult. They would appear and disappear faster than our fastest instruments can measure. Their signal would be drowned in the noise of countless other cosmic events. We might be surrounded by them, bathed in their radiation, and never know it. They could be happening right now throughout the universe, a constant quantum fireworks show too fast for us to see. Some theorists go even further. They suggest that space itself might be full of microscopic black holes and white holes, constantly forming and evaporating at the quantum scale. This quantum foam, as it's called, would make space-time itself dynamic at the smallest scales. Not a smooth backdrop for events, but a churning sea of quantum geometry. In this view, white holes aren't rare exceptions, but constant occurrences, happening everywhere, all the time, just too small and brief to notice. This quantum perspective transforms white holes from impossible objects into inevitable ones. Not the massive, stable white holes that the classical equations allow but never realize, but tiny, fleeting quantum white holes that flash and vanish like quantum sparklers. They would be nature's way of ensuring that no information is lost, that every collapse eventually reverses, that every ending contains the seed of a new beginning. As you rest there, atoms dancing their quantum dance within you, consider that you might be surrounded by invisible fireworks. Every moment throughout the cosmos, black holes might be reaching their quantum limits and bouncing into white holes. Each bounce would be a tiny victory of quantum mechanics over gravity, a brief reversal of time's arrow, a fountain of matter returning from the edge of nothingness. The quantum world has taught us that the universe is stranger than classical physics ever imagined. Particles can be in two places at once, effects can precede causes, and perhaps, at the smallest scales, black holes can become white holes, the impossible can become inevitable, and the universe can run its movie backward, if only for the briefest quantum moment. Now we turn our gaze outward, to the vast cosmic laboratory where nature conducts experiments on scales we can barely imagine. If white holes exist, even briefly, they should leave traces. Signatures written in light and gravity, clues scattered across space and time. Scientists have been searching for these clues, scanning the sky for anything that might betray the presence of these theoretical objects. It's a quest that combines cutting-edge technology with detective work on a cosmic scale. The challenge begins with knowing what to look for. A classical white hole, the kind that emerges from Einstein's equations, would be spectacular. It would glow with the light of emerging matter, surrounded by a halo of radiation from particles accelerating outward. But it would also be unstable, collecting matter at its boundary until it collapsed into a black hole. We might see a brilliant flash followed by darkness, a cosmic mayfly, living and dying in moments. Quantum white holes would be even more dramatic but far briefer. The entire mass of a black hole, released in microseconds, would create a burst of energy visible across the universe. But the signal would be so short, so intense, that distinguishing it from other cosmic catastrophes would be nearly impossible. It would be like trying to identify a specific raindrop in a thunderstorm by the sound it makes hitting the ground. Still, astronomers search. Every unexplained burst of energy, Every anomalous flash of radiation gets scrutinized. Gamma ray bursts, those mysterious explosions that briefly outshine entire galaxies, have been particular objects of interest. Some last only milliseconds, releasing more energy than our sun will produce in its entire lifetime. Could these be white holes announcing their brief existence? The evidence so far says no. We've traced many gamma-ray bursts to colliding neutron stars or exploding supernova. Others remain mysterious, but none show the specific signatures we'd expect from white holes. The spectrum of light is wrong, the duration doesn't match predictions, the gravitational effects are absent. Nature, it seems, has other ways of creating cosmic fireworks. But absence of evidence isn't always evidence of absence. Our instruments might not be sensitive enough. We might be looking in the wrong places or at the wrong times. White holes might be rarer than we imagine, or they might hide their signatures in ways we haven't anticipated. The search continues, driven by the possibility that somewhere in the data we've already collected, the signature of a white hole waits to be discovered. Some scientists have proposed more subtle signatures. If the Big Bang itself was a kind of white hole, then the cosmic microwave background, that faint afterglow of creation, might contain clues. Tiny irregularities in its pattern could reveal the white hole nature of our origin. So far, the background looks smooth, consistent with conventional Big Bang models. But each new measurement probes deeper, searching for anomalies that might reveal deeper truths. Gravitational wave detectors offer another avenue for discovery. When black holes merge, they send out ripples in space-time that we can now detect. If a black hole ever transformed into a white hole, or if two white holes somehow existed long enough to merge, they would create distinctive gravitational wave signatures. The waves would be unlike anything else in the cosmic symphony. A reversal of the usual pattern, an echo running backward. As you lie there in the quiet night, gravitational waves are passing through you. Most are from distant black hole mergers, their signatures well understood. But perhaps mixed in with these familiar signals are stranger waves. Waves from quantum bounces, from black holes becoming white holes, from processes we haven't yet imagined. Our detectors aren't sensitive enough to catch these faint signals yet, but each upgrade brings us closer to hearing the full range of the cosmic orchestra. There's also the possibility that we've been looking for the wrong thing entirely. Classical white holes might be impossible, quantum white holes too brief to catch, but perhaps nature has found other ways to create white hole-like objects. Some theorists propose grey holes, objects that mostly absorb but occasionally emit, balancing between black and white. Others imagine white holes hidden inside black holes, visible only to those who dare cross the event horizon. The search has taught us humility. The universe is vast, our observations limited, our theories incomplete. We've discovered so many unexpected things. Dark matter, dark energy, gravitational waves, that dismissing white holes entirely seems premature. They might exist in forms we haven't imagined, in places we haven't looked, at times we haven't observed. Amateur astronomers join the search, scanning the sky for unusual events. Every telescope, from backyard instruments to space-based observatories, adds to our collective vision. Data from across the electromagnetic spectrum, radio waves, visible light, X-rays, gamma rays, gets combined and analysed. Machine learning algorithms sift through petabytes of observations, searching for patterns human eyes might miss. The philosophical implications run deep. If we never find white holes, what does that mean? Does it confirm that the universe has a preferred direction, that time's arrow is absolute, that some mathematical possibilities remain forever theoretical? Or does it simply mean we haven't looked hard enough, haven't been clever enough, haven't waited long enough? Some of the most interesting searches focus on the boundaries of the observable universe. Perhaps white holes exist, but only in regions we can't yet see. As our instruments improve and our observations extend further into space and time, we might discover regions where the rules are different, where white holes can exist, where time's arrow occasionally points backward. The search for white holes has already paid dividends, even without a confirmed detection. It's pushed us to better understand black holes, to refine our theories of quantum gravity, to develop new observational techniques. The quest for the impossible has expanded our understanding of the possible. As you drift towards sleep, consider that you're part of this search. Every observation, every question, every moment of wonder adds to humanity's collective effort to understand the cosmos. Somewhere out there, white holes might be flashing into existence, too brief for us to see, but not too brief to matter. They might be teaching the universe how to recycle its information, how to balance its books, how to ensure that nothing is ever truly lost. The evidence may be elusive, but the search continues. Each night, telescopes turn toward the sky. Each day, theorists refine their predictions, and perhaps someday, in data we're gathering right now, we'll find the unmistakable signature of a white hole, a fountain in space, a reversal of time, a glimpse of the universe's hidden symmetries. Let us pause now in our journey through the cosmos and float in the quiet space between theory and reality, between what mathematics allows and what nature creates. White holes occupy a unique position in physics, objects that must exist in the equations but seemingly cannot exist in the universe. They invite us to ponder deeper questions about the nature of existence itself, about the relationship between mathematical truth and physical reality. In mathematics, white holes are as real as black holes. The equations don't discriminate. They emerge from the same solutions, follow the same rules, deserve the same consideration. In the pristine world of mathematical physics, white holes are not hypothetical or speculative. They're necessary. To exclude them would be like accepting positive numbers but rejecting negative ones, like believing in up but not down. Yet in the physical universe, white holes remain ghosts. We've never seen one, never detected their influence, never found evidence of their existence. This creates a profound puzzle. How can something be mathematically necessary but physically absent? What does it mean for something to exist in equations but not in space? This tension between mathematical and physical existence runs deep in physics. Many mathematical objects have no physical counterparts. Imaginary numbers, infinite series, five-dimensional spaces. These are tools of thought, useful for calculation but not found in nature. But white holes are different. They emerge from equations that successfully describe real phenomena. The same mathematics that predicts black holes, which we've observed, also predicts white holes which we haven't. As you rest there in the darkness, you're experiencing the reality that equations describe. Gravity holds you to Earth. That's general relativity at work. Atoms maintain their structure within you. That's quantum mechanics in action. These theories work. Their predictions match reality with extraordinary precision. So when these same theories predict white holes, can we simply dismiss them? Some physicists argue that mathematical existence is enough. In the grand multiverse of possibilities, everything that can exist does exist somewhere. White holes might be real in other universes, in regions beyond our observation, in dimensions we can't access. Our failure to find them might say more about our limitations than their existence. Others take a more pragmatic view. Physics, they argue, is about describing what we observe, not exploring every mathematical possibility. If white holes don't exist in our universe, then they're curiosities, not physics. The equations might allow them, but nature has voted with her phenomena, and white holes lost the election. But the philosophical implications go deeper. White holes challenge our understanding of time itself. In a universe with white holes, time wouldn't be the simple, forward-flowing river we experience. It would be more complex, with eddies and reversals, with regions where causality runs backward. The absence of white holes might be telling us something profound about the nature of time, that it truly does have a preferred direction, written not just into thermodynamics but into the fabric of space-time itself. The white hole paradox also illuminates the creative tension at the heart of theoretical physics. We start with observations, build mathematical models to explain them, then follow those models wherever they lead. Sometimes they lead to new predictions that we later confirm, like black holes, gravitational waves, the Higgs boson. Sometimes they lead to possibilities that remain forever theoretical. The art lies in knowing which is which. White holes teach us humility. They remind us that the universe doesn't owe us simplicity or completeness. Just because we can imagine something, calculate its properties, prove its mathematical existence, doesn't mean nature is obliged to build it. The universe is under no obligation to realize every mathematical possibility, to explore every solution, to create every theoretical object. Yet they also teach us to keep an open mind. History is littered with impossible things that turned out to be real. Atoms were once thought impossible. How could matter be made of indivisible particles? Continental drift was rejected for decades. How could solid rock flow like liquid? Black holes themselves were considered too bizarre to exist. How could gravity become infinite? Perhaps white holes await a similar vindication. Perhaps we'll discover them in some unexpected form, in some unanticipated place. Or perhaps they'll remain forever in the realm of beautiful impossibilities, teaching us about the universe not through their presence but through their absence. The philosophy of white holes extends beyond physics into metaphysics. They represent pure potential, unrealized possibility, the road not taken. In their non-existence, they define existence. By showing us what the universe chooses not to create, they illuminate what it does create. They're the negative space that defines the positive, the silence that shapes the sound. As you drift towards sleep, consider the strange privilege of living in a universe that allows us to imagine things that don't exist. We can conceive of white holes, calculate their properties, debate their possibility, all while living in a cosmos that might forbid them entirely. This capacity for theoretical thought, for mathematical imagination, for exploring the impossible, might be rarer than white holes themselves. In the end, white holes serve as a mirror, reflecting not the universe but our understanding of it. They show us the boundaries of physical law, the limits of mathematical prediction, the subtle interplay between what can be and what is. They remind us that existence is not simple, that reality is choosy, that the universe is more creative and more constrained than our equations alone would suggest. Whether white holes exist or not, their theoretical presence enriches our understanding. They force us to think more carefully about time, causality, and existence itself. They push us to refine our theories, sharpen our observations, deepen our philosophy. In their possible impossibility, they make us better physicists, better philosophers, better understanders of the cosmic dance. As we near the end of our journey through the theoretical landscape of white holes, let's zoom out and see where these mysterious objects fit in the grand narrative of the cosmos. Every piece of physics, whether real or theoretical, plays a role in our expanding understanding of the universe. White holes, even if they never step from theory into reality, have already earned their place in this cosmic story. The universe began with the Big Bang, perhaps the ultimate white hole as we have explored. From that initial emergence came everything: space, time, matter, energy, and eventually complexity. Stars formed, lived their burning lives, and died. Some collapsed into black holes, those regions where space-time curves so severely that nothing can escape. And in the mathematics that describes these black holes, white holes wait patiently, the theoretical twins that complete the symmetry. This symmetry matters, even if it's broken. It tells us that the universe's laws are more even-handed than the universe itself. The physics that governs reality doesn't prefer collapse over expansion, future over past in over out. These preferences emerge from something else, from thermodynamics, from quantum mechanics, from principles we're still discovering. White holes mark the boundary between what physics allows and what the universe chooses. In our quest to understand dark matter and dark energy, those mysterious components that make up 95% of the universe, white holes offer intriguing possibilities. Could some dark matter be primordial white holes, too small to detect directly? Could dark energy be related to the white hole nature of the Big Bang itself, a cosmic pressure that keeps space expanding? These ideas remain highly speculative, but they show how theoretical objects can inspire new approaches to unsolved mysteries. White holes also connect to the deepest questions in physics: the nature of information, the quantum structure of space-time, the ultimate fate of black holes. As we've seen, the possibility that black holes might quantum bounce into white holes offers a potential solution to the information paradox. Even if this solution proves wrong, exploring it has deepened our understanding of how quantum mechanics and gravity might reconcile. The story of white holes is really a story about boundaries, the boundaries of physical law, of mathematical description, of human understanding. They exist at the edge, in the space between what we know and what we wonder. They're part of a long tradition in physics of edge cases that illuminate the center, of extremes that clarify the everyday. As you breathe quietly in the darkness, you're part of this cosmic story. The atoms in your body were forged in stars, scattered by supernovae, gathered by gravity, organized by chemistry and biology into the thinking, wondering being you are. You're made of cosmic history, and when you ponder white holes, the universe is contemplating its own possibilities through you. The search for white holes has pushed technology forward. Better detectors, more sophisticated theories, deeper observations, all have been spurred partly by the quest to find these theoretical objects. Even if we never find a white hole, the tools we've developed in the search will discover other wonders. This is how science progresses, reaching for the impossible and finding the unexpected along the way. White holes also play a crucial role in science education and public engagement. They capture imaginations, inspire questions, make people wonder about the nature of space and time. They're gateways to deeper physics, accessible metaphors for complex ideas. Through white holes, people discover black holes, learn about space-time, encounter the strange predictions of relativity and quantum mechanics. In the multiverse of human thought, white holes have found their place. Science fiction writers use them as plot devices. Artists draw inspiration from their paradoxical nature. Philosophers ponder their implications. They've escaped the confines of physics journals to become part of our cultural conversation about the universe and our place in it. Looking to the future, white holes will likely remain part of physics whether we find them or not. If we discover them, it will revolutionize our understanding of time, causality, and cosmic evolution. If we don't, they'll continue to serve as theoretical landmarks, mapping the boundaries of possibility, keeping our theories honest, reminding us that mathematics is richer than reality. New theories of quantum gravity might predict modified versions of white holes, objects that share some properties with the classical version but avoid the instabilities. Or they might explain definitively why white holes cannot exist, closing the theoretical door that Einstein and Schwarzschild opened. Either outcome will deepen our understanding. As our observational reach extends, with gravitational wave detectors in space, telescopes that can see to the edge of the visible universe, quantum sensors of unprecedented sensitivity, will either find white holes or constrain their properties ever more tightly. Each non-detection is itself a kind of discovery, mapping the negative space of reality. The cosmic story continues, and white holes are woven into its narrative. They connect the beginning of the universe to its end, link the largest scales to the smallest, bridge the classical and quantum realms. They're knots in the theoretical fabric that, whether loosened or tightened, help us understand the weave of reality. In this grand story, you're both reader and author. Your curiosity about white holes, your wondering about their existence, your journey through these ideas tonight. All of this adds to humanity's collective exploration of the cosmos. We are the universe trying to understand itself, and white holes are part of that understanding, whether they exist in space or only in thought. And now we arrive at the edge of our journey, though in truth we've been here all along, for white holes exist at the edge of possibility, of understanding of what the universe allows. They embody the eternal questions that drive physics forward. What is real? What is possible? What is the relationship between mathematical beauty and physical truth? These questions have no final answers, only deeper understandings. Each generation of physicists pushes the boundaries a little further, sees a little more clearly, yet always finds new mysteries beyond. White holes represent this eternal frontier, the horizon that recedes as we approach, the questions that deepen as we explore them. Why does the universe allow black holes but seemingly forbid white holes? This question touches the heart of physical law. It's not enough to know the equations. We must understand why nature chooses some solutions over others. The answer might lie in thermodynamics, in quantum mechanics, in principles we haven't yet discovered. Or it might lie in the nature of existence itself. Perhaps being is fundamentally different from becoming. Perhaps reality has an inherent direction that mathematics alone cannot capture. The question of white holes is really a question about time. Why does time flow forward? Why do we remember the past but not the future? Why does entropy increase? These mysteries are all connected, all facets of the same deep puzzle. White holes, with their reverse time flow, their decreasing entropy, their paradoxical nature, force us to confront these questions directly. As you rest there in the embracing darkness, you are embedded in time's flow. Your thoughts move from past to future. Your memories accumulate. Your experiences build upon each other. This forward flow feels so natural, so inevitable, that imagining it reversed seems absurd. Yet the equations that govern the universe don't share this bias. They work equally well backward and forward, leaving us to wonder why nature chose one direction over the other. Perhaps the absence of white holes is telling us something profound about consciousness itself. We are creatures of time's arrow, beings that exist in the flow from past to future. Our ability to think, to remember, to plan, all depend on time's reliable direction. In a universe with white holes, with regions where time flows backward, could consciousness as we know it exist? Are we here, able to wonder about white holes, precisely because they're not here? The eternal questions extend beyond physics into philosophy. What does it mean for something to be possible but not actual? Are mathematical objects real in some Platonic sense, or are they merely useful fictions? When we discover a new solution to an equation, are we inventing or discovering? White holes sit at the intersection of these ancient debates, challenging us to think more deeply about the nature of mathematical and physical reality. There's beauty in unanswered questions. They keep us humble, curious, engaged with the mystery of existence. If we knew everything, if all questions were answered, something essential would be lost. The unknown is not just what we haven't discovered yet. It's the space for wonder, for possibility, for the creativity that drives science forward. White holes remind us that the universe is stranger than we imagine, perhaps stranger than we can imagine. Who would have thought that space could curve, that time could dilate, that particles could be entangled across cosmic distances? Each of these discoveries seemed impossible until it wasn't. White holes might join this list, or they might remain forever in the realm of beautiful impossibility. Either outcome teaches us something valuable. The search for white holes is part of humanity's larger quest to understand our cosmic context. We want to know where we came from, where we're going, what's possible in the vast spaces between. White holes offer one possible answer, that the universe recycles, that information is preserved, that every ending contains a beginning. Even if this answer proves wrong, the questioning itself enriches us. As you drift towards sleep, carried by the gentle rhythm of your breath, remember that you are part of this eternal questioning. Every time someone wonders about white holes, the universe wonders about itself. Every thought about reverse time, about cosmic fountains, about mathematical possibility adds to our collective understanding. We are all philosophers when we ponder the impossible, all scientists when we seek evidence, all poets when we marvel at the mystery. The questions white holes raise will outlive us all. Future generations will bring new tools, new theories, new perspectives to these eternal puzzles. They might discover white holes in forms we can't imagine, or they might prove definitively that they cannot exist. But the questions themselves about time, existence, possibility will remain, taking new forms, inspiring new searches, driving the eternal human quest to understand. Perhaps that's the greatest gift of white holes. Not answers, but better questions. They teach us to question our assumptions about time, to probe the foundations of physical law, to imagine alternatives to the reality we experience. They keep us intellectually humble and curious, always ready to be surprised by the universe's next revelation. In the end, white holes are mirrors that reflect not the universe, but our understanding of it. In their theoretical existence and possible non-existence, we see the boundaries of knowledge, the interplay of mathematics and nature, the eternal dance between what we can imagine and what is. They remind us that the universe is not obligated to be simple, complete, or fully comprehensible. It is what it is, and we are privileged to wonder about it. And so we come to rest at the end of our journey through the land of white holes. Though in the world of ideas no journey truly ends, we've travelled from the mathematical necessity of these cosmic fountains to their physical improbability, from their quantum possibilities to their philosophical implications. We've seen how they complete the symmetry of Einstein's equations while seemingly violating everything we observe about the universe's preferred directions. White holes have taken us to the edge of black holes where space curves beyond return, the edge of time where past and future lose their meaning, the edge of existence where mathematics and reality negotiate their boundaries. We've discovered that these theoretical objects, whether they exist or not, illuminate the deepest principles of physics, the conservation of information, the arrow of time, the quantum nature of space-time itself. You've learned that white holes might be impossible in our universe, forbidden by thermodynamics and quantum mechanics, too unstable to survive even microseconds in the real world. Yet you've also seen that they might exist in forms we haven't imagined, as quantum bounces of dying black holes, as the Big Bang itself, as fleeting fountains that preserve the universe's information in ways too brief and scrambled for us to detect. Most importantly, you've discovered that the question of white holes is really a question about questions themselves. Why does the universe choose some mathematical possibilities and reject others? What is the relationship between theoretical beauty and physical truth? How do we understand existence in a cosmos that allows us to imagine impossible things? As you lie there, perhaps drowsier now than when we began, you carry with you the strange comfort of mystery. The universe doesn't reveal all its secrets at once. It keeps some possibilities forever theoretical, some equations forever unrealized, some symmetries forever broken. And in that holding back, that selective revelation, we find not frustration but wonder. Your journey tonight has been both cosmic and intimate. You've travelled to the edge of black holes and the beginning of time, yet never left the quiet sanctuary of your rest. You've pondered the impossible while breathing the very possible air of Earth. You've been, in your wandering, a white hole yourself, a source of questions flowing outward into the darkness, seeking their own answers. The night continues its slow turn around you. Stars wheel overhead, some perhaps harbouring black holes, none revealing white holes, all participating in the cosmic dance of gravity and light. And you, made of star stuff, carrying the history of the universe in every atom, rest at the centre of your own small cosmos, dreaming perhaps of theoretical fountains and reverse time. If you've enjoyed this gentle exploration of the impossible, I hope you'll give it a soft like, a quiet acknowledgement that wondering about white holes has been worth these moments stolen from sleep. And if you'd like more journeys to the edges of physics, more quiet explorations of cosmic mysteries, consider subscribing. There are always more questions waiting in the darkness, more theoretical wonders to explore with drowsy curiosity. Share in the comments where you're listening from, your city, your country, your small corner of this improbable universe. Are you in a place where the night is deep and stars are visible? Or somewhere bright with human-made light, pushing back the darkness with electricity and ambition? What time is it where you are? How does the universe look from your particular vantage point tonight? Remember, this video has been for wonder and rest, for education and relaxation. It's not medical advice for sleep troubles or philosophical counsel for existential questions. It's simply a place where physics and peace coexist, where the impossible can be pondered without urgency, where questions matter more than answers. Thank you for spending this time with white holes and with me. Thank you for bringing your curiosity to these theoretical shores, for allowing yourself to wonder about cosmic fountains that probably don't exist, but definitely make us think. Your attention has been a gift, your company a pleasure, your wondering a contribution to humanity's endless exploration of what might be. As you drift now towards sleep, or toward whatever rest awaits you, carry with you the gentle paradox of white holes. They are impossible yet necessary, absent yet illuminating, theoretical yet somehow deeply real in their ability to make us question reality itself. They are perhaps the perfect bedtime story for a universe that keeps its biggest secrets wrapped in mathematical beauty. May your dreams be filled with gentle fountains of light, with time flowing in all directions, with the peaceful impossibility of existence itself. May you rest in the comfort of not knowing everything, of living in a universe still capable of surprise, of being a conscious part of a cosmos that generates both black holes and the minds capable of imagining their opposites. Sleep well, dream deeply, and remember, in a universe vast enough to contain black holes, strange enough to allow quantum mechanics, and beautiful enough to be described by mathematics, perhaps there's room for white holes too, if only in the infinite space of possibility that exists between our theories and our dreams. Good night, and may all your theoretical journeys lead you to peaceful rest.